In this video, I'm going to go through AQA A-level, AS chemistry. So AS paper, the paper 2 from May 2018. I'll just do the first half of the paper, questions 1 to 6, in this video, and carry on with in the second video. Okay, the first one about rates of reaction. Hydrogen peroxide solution decomposes slowly to form water and oxygen, according to this equation here. Okay, 3 experiments are shown in table 1 to investigate how the volume of oxygen produced varied over time under different conditions. And the mass of the catalyst was used was the same in each experiment. Okay, and right. Now I'm actually going to start off with question 1.2 rather than 1.1 here, and you'll see why in a minute. Right. So draw 2 lines on figure 1 here to show the volume of collected, how that varies with time in experiments 2 and 3. So this black line here they've shown that's experiment 1, and we've got to show them for experiment 2 and 3. Well, let's look at experiment 1. We've got concentration of hydrogen peroxide, and experiment 2 are the same volume of hydrogen peroxide. That means it's going to give us the same final volume of oxygen. But in the case of experiment 2, the catalyst is powdered, so it's going to have a bigger surface area, so it's going to be more effective, so the rate of reaction is going to be faster. So for experiment 2 then, the line is going to be steeper because the rate is faster, but the amount of oxygen produced is going to be the same. Let's compare experiments 1 and 3 now. Well, they've both got catalyst is present as lumps, and it's the same, so that's going to have the same surface area. The concentration, though, in experiment 3 is only half of that in experiment 1, so that's going to give us a slower rate of reaction. Also, because there's the same volume of solution, you've only got half the moles of hydrogen peroxide in experiment 3, so you're going to only make half the amount of oxygen. So that graph is going to be slower, and it's only going to reach up. The final volume of oxygen is going to be lower than in experiment 1. So there's experiment 3. Okay, so now let's go to experiment 1.1, sorry. Explain in general terms how a catalyst increases the rate of reaction for 2 marks. Well, all I want you to say is 1 mark provides an alternative route. An alternative mechanism, if you like, with lower activation energy. So that's a fairly standard question. Experiment 1.3. Explain in terms of collision theory the effect of increasing concentration of hydrogen peroxide and the rate of reaction. Okay. So if in this case, we've got a catalyst. If you increase the concentration, you increase the number of collisions between molecules. Keep it fairly vague. In order for a reaction to occur, a collision needs to happen. So more collisions, higher rate of reaction. Okay, so now here is a question. It's a titration question with quite a bit of practical details here. So you sort of require practicals too. You'll need to use for this. Okay, so citric acid is in fruit, blah, blah, blah. A student analyzed a sample of citric acid to determine its percentage purity. So he dissolved some citric acid in water and dissolved it in a volumetric flask. We'll come to that later. He took out 25 centimeter cube samples of this, and they titrated against sodium hydroxide of this concentration using phenolphthalein as an indicator. Okay. Right, so there's the equation which we'll need later. So it's 1 mole of citric acid to 3 moles of sodium hydroxide. I'll come to that later, I think. Okay, so let's just draw a little sketch of what the student did here. So he had the burette, or she had the burette there with NaOH in it. had a conical flask. With the citric acid in there, 25 centimeters cubed. All right. The student rinsed the burette before filling it with sodium hydroxide solution. State why the student should use sodium hydroxide solution rather than water for the final rinse of the burette. Well, if he didn't do that, he would have little bits of water stuck to the side of the burette, and he would effectively dilute the sodium hydroxide solution. It wouldn't be quite as strong as he thought it was. The student carried out several titrations, and the results are shown in table 2. Complete the table to show the titer. So I've done that, subtracted the initial reading from the final reading. All right, and question 2.3, a pretty standard question. Calculate the mean titer using the concordant results. Now, concordant results must be within 0.1 centimeter cubed of each other. So there's only 2 there are concordant. That one, number 1, and number 3. If you calculate a mean of that, even I can do that without a calculator. It is 23.95 centimeters cubed, and that's the appropriate number of significant figures. Percentage errors then now. The total uncertainty when using the burette is plus or minus 0.15 centimeters cubed. This is the combination of uncertainties taking 2 readings, okay? Use the answer from 2.3 to calculate the percentage uncertainty. So, right, the error we've got is 0.15 centimeters cubed, and the total volume is that. So divide by that, multiplied by 100. That's going to give us a pretty small error. Of 0.6%, 0.63%. Okay, now I pasted the information again here, because so what we've got to do, use your answer to question 2.3, that's the titer, to find the mass in milligrams of citric acid dissolved in the solution. Okay, so let's just read what it says here now. So they made up a solution, a 250 solution in a volumetric flask, and they put in there 784 milligrams, let's put that in grams, 0.784 grams of citric acid. Then they took out 25 of that, put it in the conical flask, so a tenth, and they titrated against NaOH, and the NaOH has got a concentration of 0.05, and the volume they needed for that was the titer, 23.5 centimeters cubed, 23.95 centimeters cubed. Right, so let's do that then. What we're going to do first of all is work out the moles of NaOH in the titer. So that's concentration times volume, 0.05 multiplied by 23.95 over 1,000. That's got to be in dm cubed, don't forget. And that is going to give us a value of 3.99 times 10 to the minus 4 moles. Sorry, 1.195, beg your pardon. .1975 times 10 to the minus 3 moles. Right, now we have to work out how many moles of citric acid we had in there. Okay, so there's our citric acid in there, reacted with the NaOH. We need to look at the ratio. 1 mole of citric reacts with 3 moles of sodium hydroxide. So the moles of citric acid is going to be equal to that number divided by 3. And that is equal to 3.99 times 10 to the minus 4. Now that's the moles of citric acid in 25 centimeters cubed. We want to find out how much the total mass of citric, the total moles of citric acid we've got in 250. So we're just going to multiply that by 10. I'll go over here now. So moles citric acid in 250 is going to be equal to 3.99 times 10 to the minus 4 times 10, 3.99 times 10 to the minus 3. Now we need to work out the mass of citric acid. All right, now we do that by moles equal to mass. Okay, so we're going to do mass of citric acid, moles times mR, 3.99 times 10 to the minus 3 moles multiplied by, they give us the the mR of citric acid. Where's it gone? I gave it as a question. I think I haven't pasted that bit, but they do give it you. You don't have to actually work it out because they tell you it is 192 for citric acid. They tell you that in the question. So do that and you get an answer of 0.7664 grams. Now it wants you to work it out into milligrams multiplied by 1,000, so that gives you 7. Let's give it to 3 significant figures because all the data is given to 3 significant figures. So that's 766 milligrams. All right, now we need that for the next question. Okay. So calculate the percentage purity of the citric acid. So the percentage purity is equal to the real mass, is the mass of citric acid divided by the total mass of the impure solid times 100. Well, we worked out we've got 766 milligrams of citric acid, but the total mass of solid, it told us in the question, dissolved was 784 milligrams. Multiplied by 100, that gives us a purity of 97.8%. That's the 3 significant figures. Okay, so question 3. Okay, about enthalpy changes. Ethanoic acid reacts with sodium hydroxide. There's the reaction, and the enthalpy change, delta H, is minus 5061 kilojoules per mole. Well, that will be per mole of the acid and the NaOH because it's a 1-to-1 ratio. It makes things simpler. Okay, calculate the temperature rise when 25 centimeters cubed of ethanoic acid, or 2 molar, reacts with the same volume and the same concentration of sodium hydroxide. That's quite useful because we know neither one is in excess. We're going to have the same moles of both of those, and they react in a 1-to-1 ratio. We have the same moles because we've got the same volume and the same concentration. Okay, now which equations are we going to need for this? We're going to have to use Q is equal to MC delta T. That will give you the quantity of heat. I'll say what this stands for in a minute. The quantity of heat released in the experiment. And then we need to convert Q to a value of delta H. So delta H is going to be equal to the Q divided by the moles reacted. Now the moles reacted, we can either use the moles of citric, of ethanoic acid, or of NaOH because it's the same for both. Okay, now we don't add the moles together. It's kind of like per mole of equation. It's delta H is the enthalpy change when 1 mole of that reacts with 1 mole of that to give 1 mole of that and 1 mole of water. Okay, right, so let's see where we can start with that. Right, let's work out our moles. We need to work out the moles of NaOH first. Let's do that. Right. Okay, so the moles of NaOH, we could equally use the ethanoic acid, is equal to concentration times volume, which is equal to 2 mole per decimeter cubed, volume 50 over 1,000 in dm cubed. So that gives us 0.1 mole, 0.0, sorry, 0.0, that's 25 centimeters cubed. (25 over 1,000 in dm cubed). That gives us an answer of 0.05 moles. Right, now we can put that into our expression for Q here. Let's work out what Q is from this one. So we're going to say that Q is equal to the delta H, which they give us, multiplied by the moles. I've just rearranged that equation. So Q is equal to delta H here. Now we need to convert that into kilojoules, sorry, into joules. It's in kilojoules at the moment. So that's the reason why we need to convert that into kilojoules, is because the specific heat capacity of water is measured in joules per Kelvin per gram, not kilojoules. Okay. Now we're not going to worry about the minus sign. The minus sign just tells us that it is exothermic, so the temperature is going to go up. Okay, so we've got 5,100 multiplied by 0.05, which gives us the quantity of heat released in the reaction is 2,805 joules. Now we've got a value of Q, and we need to put that into this equation here so we can work out the value of delta T, which is what it's asking us. Okay. Right, so let's rearrange this equation. So we get delta T is equal to Q divided by M, that's the mass of the solution, multiplied by the specific heat capacity C. Now the mass of the solution, we've got 25 centimeters cubed of ethanoic and 25 of that, and the density is 1 gram per centimeter cubed, so the total mass, that's equal to 50 grams of solution. So we're going to put the numbers in there. We get 2,805, which we worked out from here, divided by 50 multiplied by 4.18, the specific heat capacity of water. Put the numbers in there, we get 13.4 degrees C, and we know that that is going to be a temperature rise because, as I said, Q here, delta H is exothermic. It's got a negative there, so that's the answer to that. And 3 significant figures, I think, well, 1 decimal place is appropriate there. Okay. Okay. Now this is relates to practical, require practical. I think it's number 2, yeah, where you have to measure an enthalpy change. A student recorded the initial temperature of the ethanoic acid in the polystyrene cup for 3 minutes, and at the 4th minute they added the sodium hydrogen carbonate, which is solid. The student stirred the mixture and carried on recording the temperature every minute. The student's measurements are shown in figure 2. A best fit line showing the temperature before mixing has been drawn. Draw an appropriate best line to show how to find the temperature change at the time of mixing. Okay, so here's the graph they're giving us. So it's an endothermic reaction here. So they've drawn their first line of best fit. Now we need to work out delta T at what it would be at 4 minutes when we added the solid, when they didn't take a temperature reading there. So you can see these are forming quite a nice curve. So I'm just going to carry on with that curve and extrapolate that down to there. This one here is not an anomalous reading. The reason why it's there is because not all the reaction has happened there. Yeah, it's the sodium hydrogen carbonate hasn't all reacted with the acid, so the temperature hasn't reached its lowest point. It's still going down. And the point of saying that is, well, why is this warming up here? Well, it's absorbing heat from the surrounding. It's getting a little bit warmer. So we're saying if it had been absorbing heat at that rate, at this point, 4 minutes, the temperature would have been there. So we're going to measure our delta T by doing that there. Okay, And so that's going to be 17.1 for that value up here, minus 11.1, which gives us 6.0 degrees C is the temperature rise. So that, as I say, that relates to a standard, one of the required practicals, and it's a sort of standard way of adjusting for heat loss or heat gain during an enthalpy change experiment. Okay, question 4, onto organic question. Right, alkanes nonane and 2,4-dimethyl-heptane are structural isomers, but they've both got the formula C9H20, if you count everything up. Right, state the general formula of an alkane containing N carbons. Well, the general formula is CnH2n plus 2. It's fairly standard. And deduce an expression for the relative molecular mass in terms of N. Well, carbon weighs 12, so what I'm going to say is the carbon bit, that's going to be 12 times N. Hydrogen weighs 1, so the hydrogen bit is going to be plus 2N, and then we've got plus 2, so that simplifies as 14N plus 2. That's the MR of an alkane, where N is the number of carbon atoms. Okay. Right, explain why nonane has a higher boiling point than 2,4-dimethyl-heptane, even though they've got the same molecular weight. Well, what kind of intermolecular forces are we getting here? Well, C and H, they've got the same electronegativity, so we're not going to have any dipole-dipole interactions, so we're only going to have van der Waals forces between molecules, and they're stronger in nonane because, if you like, the molecule has got a bigger surface area, so there are more points of contact. When it's branched, it reduces the surface area of the molecule. Remember, van der Waals forces are, van der Waals force you might want to put are, they are dependent on fluctuations in the negative charge cloud. So the more electrons a molecule has, the stronger they are, but they've also got to be able to touch each other. Okay, so these, I've given far more than you actually need for 2 marks there. Okay. Right, let's move on. Equation for the complete combustion of nonane. That's a fairly standard question. So we've got C9H20 plus oxygen. Complete combustion, we're going to get CO2 and water. We're going to have, we've got 9 carbons on the left, so we must have 9 CO2s. We've got 20 H2Os on the left, so that means 20 hydrogens on the left, so that means we're going to need 10 H2Os. So how many carbons altogether? Well, how many oxygens to balance? We've got 18 in the carbon dioxide, we've got 10 in there, which is equal to 28. So that means we need 14 O2s to balance it. Nonane is found in fuel for jet engines. Combustion produces pollutants including nitrogen monoxide. Explain how nitrogen monoxide is formed. Well, at the N2 and oxygen react to form NO. Nitrogen is in the air, oxygen's in the air. This can only happen because there must be very high temperatures in the processes, in the burning of the fuel in the jet engine. You need really high temperatures to make the nitrogen react. Nonane can be cracked to form large quantities of propene, right? If you want alkenes, what kind of cracking do you use? It is thermal cracking. It's not catalytic cracking, which would give more branch chain alkanes. Okay, 4.6, the main use of propene formed from cracking is to make polypropene. Draw the repeating unit of polypropene. Right, that is a bit more difficult than it sounds because, right, let's just think about ethene. What happens with ethene? Polyethene. Right, you get loads of ethene molecules next to each other. you break the double bond between them and you form a new bond there. Now with polypropene, it's very similar, but all we have to do to make propene is to get rid of one of those H's and put a CH3 there. Okay, so the repeating unit is going to we're going to break the bond, so it's going to be like that. On one carbon we've got 2 hydrogens, and on the other carbon we have got a methyl group and a hydrogen. That is the repeating unit, like that. Okay, now a lot of people will get a bit confused there and write this as the answer. Okay, and you can see that that is not right. Okay. Okay. Right. Next question. We're on to question 5 now. Right, hydrocarbon, to give us percentage mass, and okay, that determine the empirical and molecular formula of this hydrocarbon. Okay, now hydrocarbon means it contains only carbon and hydrogen. So how are we going to do that? Well, I'd like to say in 100 grams, we would have 87.8 grams of carbon, and the rest of that, the other percentage, is all hydrogen. So that's going to be 100 minus 87.8, which is 12.2 grams of hydrogen. Right, to work out the empirical formula, we need the ratio of moles. So moles is equal to mass over mR. Well, it's AR in this case because we're talking about atoms. So how many moles of carbon have we got? We've got 87.8 divided by the AR of carbon, 12 to 12.2 divided by 1 for hydrogen. Do that on a calculator, you get 7.316 to 12.2. If you want to simplify a ratio, you divide by the smallest number, which is of course 7.31. So we're going to get 7.31 divided by 7.31. Sorry, yeah, that's right. 6 to 12.2 over 7.316. Do that on a calculator, we get 1 to 1.66. Now that's like 2/3, isn't it? So I'm going to multiply that by 3 to give us a whole number ratio. So 3 times 1 gives us 3. 3 times 1.66 gives us 5. So the empirical formula, that's the simplest ratio, is C3H5. Now you can tell from that you can't have a compound with that formula because the carbons are not forming the right number of bonds, but they tell us here that the MR is actually 82. So remember, the molecular formula isn't the simplest ratio. That gives us the actual numbers of carbons. So it could be a multiple of this. So let's double that and see what we get. We get still the same ratio, but C6H10. And if you work out the MR of that, you'll find out the MR of that is 12 is actually 82, which they tell us there. So that is our molecular formula. Okay. Now suggest 2 possible structures for this. Okay. Right. Now let's just do this last bit here where it says the bromine water will react with that. It must have double bonds in it. Okay. What kind of reaction is that? When Br2 reacts with it, it's an addition reaction. It's actually electrophilic addition, but I'll just write addition. It's an addition reaction. The bromines add across the double bond. Right, let's suggest 2 possible structures there. Okay, so if we look at that, we've got C6H10. Now, if it was an alkane, it would be C6H14, 2N plus 2. So if it had 1 double bond, it would be C6H12, but it's not. If it's got 2 double bonds, is going to be C6H10, which is what we've got. So you can draw any structure with 2 double bonds in it, or important to realize here, or having 1 double bond is like having a cyclic. If you've got a cyclic ring, then you lose 2 hydrogens for that. So we could have, I'm going to draw the skeletal formula. We could have a cyclic compound with 1 double bond in it. You could have that. Now, if you just count your number of hydrogens there, just to convince yourself, you've got 2, 4, 6, 8, only 1 there, 9, and 1 there, 10. So that's fine. So you could have that. And the other thing, you could have a straight chain one. Okay, so you could have a straight chain, just draw 6 carbons, and you can put double bonds anywhere you like. Let's put 1 there and 1 there, and the right number of hydrogens. So you need 2 there, 1 there, 2 there, 2 there, 1 there. All right, you should write hydrogens on, otherwise they won't give you the mark, unless it's a proper skeletal formula. If you wanted to write that as a skeletal formula, then you could do 1, 2, 3, 4, 5, 6, double bond there, double bond there. And there's other structures you can have there, but that's just 2 possible ones. Okay, 6. Compound A is a halogenoalkane. Name the compound A. Right, so it's 6 carbons long, so it's going to be so it's 5 carbons long, so it's going to be pentane. That's the longest carbon chain, and it has got a chloro group and number 3, so it's 3 chloro, but it's also got 2 methyl groups, one on number 2 and one on number 4, so it's 2,4 dimethyl. We've got those 3 bits in the name to put together. Well, the chloro bit should go first. That's the functional group. So it's 3 chloro, 1, 2 dimethyl pentane. Okay, right now, compound A, which is our, which we said there was, it's C7, you counted up, it's C7H15Cl, okay, has got a relative molecular mass of 134.5. Draw the peaks for the main molecular ions in the spectrum of A, the mass spectrum of A. Right, now it tells us we can just presume that all the hydrogen is 1H and all the carbon is 12, but we have to be careful with chlorine because chlorine is a mixture of 2 isotopes. It's 35 and 37, and they are, you find them in a 3-to-1 ratio, 75% to 25%. Okay, so we need to think then, although the MR of this is 134.5, we will get nothing on the spectrum there of 134.5 because that's an average molecule, so you're not going to see anything at all there. All the molecules you've got, they're either C7H5 35Cl, or they are C7H, not 5H15, sorry, 37Cl. Now, if you work out the MR of that one, it works out to be 134. And of course, the MR of this one's going to be 2 more. That's 136. Now, it tells us that the 35 chlorine is 75%. So that's 3/4. So that means only 25% is that one. So on our graph, we need to draw 2 peaks, one at 134 and one at 136. And the one at 136 is going to be 3 times, so the one at 134 is going to be 3 times higher. Three times higher, so we'll draw that, and we have got 134 and 136 is there. Right. 6.3, reaction of A with dilute aqueous sodium hydroxide. Right, when you've got, and so NaOH, you're going to get nucleophilic substitution. Right, that's when you've got aqueous sodium hydroxide, OH minus AQ. And in the next part of the question, they're going to do it with NaOH in ethanol. And the same reagent, but completely different reaction. With this one, you're going to get elimination. Okay, and that's in the second part of the question. But for the time being, we'll just do what happens with the aqueous NaOH. We're going to outline the mechanism, curly arrows. So we are going to have here OH minus. Now there's 3 lone pairs on the oxygen, but you only need to draw 1 because there's only 1 reacting. Right, and that's going to go for the positive, delta positive carbon there. I'm going to draw that out because it's going to obscure the details. Of that carbon is delta positive, so the curly arrow goes onto there. That carbon is now going to be forming too many bonds, so one's got to break. So the pair of electrons in that bond, draw it from the bond onto the chlorine there. So that's the mechanism, and we just need to draw the product, which is going to be I'm not going to draw out the whole product. I'll just draw. So it's going to be 5 carbons long, not 6 like I've drawn. Okay. And the Cl has been replaced by an OH minus there. And then you've got all the other stuff there, which I won't bother drawing on. Okay. Now the next question I think does ask about the elimination reaction. Okay, so reaction of A with hot ethanolic potassium hydroxide. Okay, so the OH minus ions are now in ethanol solution, gives alkane C. Okay, alkene C. So we're going to get an elimination. Okay, name the mechanism. So it's elimination. And the role of the hydroxide ions here, they don't behave as nucleophiles here. They behave as bases. And bases, we don't have to write this down, are proton acceptors, which is a bit tricky at AS because you haven't really done about acids and bases that much. But OH minus is a proton acceptor. Now what happens is, outline the mechanism. Well, if you remember, when you eliminate, you lose the halogen atom and a hydrogen from the carbon next door. Now this is symmetrical, so it doesn't matter which one you choose. I'm going to draw that one, but if it chose that one, that would be fine. It's the same. So it removes chlorine and hydrogen from the one next door, and then you form a double bond between those 2 carbons there. That's how it goes. Right, so let's draw that mechanism. Right, so we've got OH minus. And there's a lone pair on the OH minus. There's 3, but I'm only drawing 1. That's going to form a bond to that hydrogen. Now that hydrogen can only form 1 bond, so that means the pair of electrons in this bond are going to be lost, and they go like that to form the pi bond between the 2 carbons. And of course, this carbon is now going to be forming too many bonds, the green one, so you've got to lose, you've got to break one of the bonds, and so the electrons in the bond there go onto the chlorine. Okay, so we got our alkene, 5 long, and we have got our double bond there. Just put the hydrogens on here. So that's a methyl group there, isn't it? And a methyl group there. And we are going to get H2O and Cl minus. The H2O comes from the hydroxide ion, picking up an H+. Okay. So that's the mechanism there. 6 marks for that. It's a harder mechanism than the other one. Yeah. Okay, infrared spectrum in figure 4 is either alcohol B or alkane C. Tick the box that shows the correct compound. Right. Is it the alkene or the alcohol? Right. what we're going to do when you look at the spectrum, so everything here you kind of ignore because that's the fingerprint region. Look at your infrared absorption data. Right, if it was an alcohol, you would have an absorption in that region here, which is around about here, and you don't have that. Okay, so it's not an alcohol. Let's confirm. Do you have this absorption for the alkene? You do. You've got that little peak there, and it is quite often quite small and quite shallow, that alkene peak, that one there. So we're pretty sure that that is the alkene. And to me, what is more obvious that makes it the alkene is not the green peak there, but the absence of this peak here. And I've just, for comparison, there's the spectrum of an alcohol, and you can see this is the OH peak. It's very, very easy to spot, and it's right next door to this peak here, which, if you look, is the CH peak. CH gone on this. There you go. It's there. Okay, and you've got the CH and that one there, and it's very characteristic. That this green peak is very characteristic of an alcohol, and that sort of double dip because it's next to the CH. Really easy to spot. By the way, CH peaks in red, they're not very useful because almost every organic compound has a CH in it, doesn't it? Okay. Right. A and D react with aqueous sodium hydroxide, so that's going to be a nucleophilic substitution to make the alcohol. Okay, which one will react? Well, D reacts much more quickly than A. Why? Now, this is because the alkane is bromine and not chlorine. Why do bromoalkanes react more quickly? Because the carbon-bromine bond is a lot weaker than the carbon-chlorine bond, and that is what determines the rate of reaction. Right, and that is the end of question 6. It's about halfway through the paper. I will carry on with that in the next video.